Would you believe me if I told you that some of the challenges with extracting usable energy from deep underground were the same as some of those for extracting energy from the sun? Well, it's true. Geothermal energy and solar thermal energy face some of the same basic challenges of capturing thermal energy from natural heat sources. Interestingly, geothermal energy is one of the few energy sources that you can't trace back to the sun. Geothermal energy can be used for direct heating, like in buildings or hot water systems, or in electricity production. It is typically considered a renewable resource, although it is possible to use the heat faster than it can be replenished. As with all energy sources, when looking at electricity production from geothermal energy, we need to consider whether it's a good fit for our situation. This includes looking at things like efficiency, cost, and key technology-specific variables. Using geothermal energy is all about taking advantage of the heat being stored and generated from both the radioactive decay of elements inside the Earth and from the original formation of the planet. This heat creates molten rock, steam, and hot water. Steam is generated where groundwater is trapped by impermeable rock and there is a heat source, such as hot rocks or magma, close by. But how do we actually utilize the energy from geothermal resources? To date, we've mostly used the heat in the form of steam or hot water where it comes close to the surface. This makes it easy for us to use for direct heating and because we know how to use the steam to make electricity. You can tell where there is steam close to the Earth's surface because there are geysers, steam wells, and hot springs, and usually this occurs along fault lines. Traditional geothermal energy generation begins by drilling wells to release the hot water or steam from its reservoir in a way that we can control. After that, there are a few options when it comes to making electricity from geothermal energy, and it all depends on the steam or water quality. Just so you know, sometimes the water is salty from the minerals underground and it's referred to as brine. But back to how we access geothermal energy. Well, in this diagram we have drilled a well into a reservoir of what is called dry steam. This just means that the steam is superheated so it won't condense in the turbine. Once we bring the steam to the surface, we can pass it straight through a turbine connected to a generator to produce electricity. After this, some of the steam will be condensed back into water and injected back underground to replenish the reservoir, while some of the uncondensed steam may simply be released to the atmosphere where it can't do any harm. A second way to use geothermal energy is to bring hot water to the surface and put it in something called a flash tank. The flash tank is at lower pressure than the water was, and so most of your hot water boils and becomes steam. In this case, we make wet or saturated steam, which will condense into water once it passes through the turbine to generate electricity. The hot water can be re-injected back underground to get reheated. Just remember that you will need a different sort of turbine to deal with the wet steam. Finally, there are binary cycle plants. This is where we decide to bring hot water up to the surface, but rather than use that water directly, we choose to put it through a heat exchanger to heat up a different working fluid to send through the turbine. That working fluid is usually something other than water. It might be a refrigerant, like in the back of your fridge, or inside your air conditioner. Typically, it would be something that has a lower boiling point than water, so that we can take advantage of the lower temperature heat source. Remember that steam works best for high temperature heat sources, like you might get from burning biomass. Binary plants may also be used where the water is so corrosive or salty that it will cause problems with your equipment. The binary cycle is the most common approach for geothermal electricity. The amount of electricity you can get from geothermal energy is limited by the temperature you get from your reservoir, the flow rate from your reservoir, and your condenser if you have one. So, what sort of efficiency can we expect from geothermal energy sources? Well, it's really low, only about 5 or 10%. If you look at the diagram, we have efficiency on the y-axis and the top cycle temperature on the x-axis. The unbroken curve at the top of the chart is the ideal or Carnot cycle efficiency. You can see geothermal energy is way down in the 5 to 10% range due to the lower temperature of the water or steam we extract. By comparison, gas turbines are sitting up there at 50 to 55% because they are operating at much higher flame temperatures. Nuclear power plants typically operate at lower temperatures, but the efficiency is in the 30%. Even the oldest coal technology, subcritical coal, is around 30 to 35%. If your hot temperature is relatively low, then there's only so much energy you can ever extract because the difference between your hot temperature and your cold temperature will never be that big. So this means your maximum efficiency or Carnot efficiency will be low, which means your actual efficiency will be even lower. Cost is something else to think about when you look at different ways to generate energy. The cost of a geothermal plant is affected by the cost of exploration, the depth of the well, plant costs, and operating and maintenance costs. This diagram shows an approximate levelized cost of electricity for geothermal systems. You can see that well completion is by and large the largest part of the cost of geothermal power plants. It also shows that a way to bring costs down is not with improved equipment, but by increasing the flow of water out of the reservoir. But how do you increase the water flow out of a geothermal system? One of the ways to increase flow out of the reservoir is to use what we call enhanced geothermal. This is where we don't just use the hot spring that we have close to the surface, but we fracture or stimulate the geological system. Here you need to drill 2 wells and then stimulate or fracture the rock to connect the 2 wells. Cold water is injected into one well where it is heated and then withdrawn via the other well. The geology can differ for enhanced geothermal systems, and in some cases we can even use hot but dry rock formations. However, enhanced geothermal systems are typically more expensive due to the drilling, and it's really difficult to get control where the hot water goes. One of the advantages of geothermal is that it's dispatchable. This means that it's readily controlled and you can more or less generate electricity on demand, which is not overly common among the suite of renewable electricity sources. You may have guessed from our discussion that the key variables for geothermal resources are temperature, water flow, and depth. Temperature is important because it determines efficiency. Water flow is important because it determines the power output, and well depth is important as it is a major contributor to capital cost. So whilst there are cost and resource challenges, geothermal remains interesting because it's dispatchable and because of its potential to be used for direct heating. It may not have the same growth rate as some of the other renewables, but geothermal definitely has a place in a low-carbon future.